Hello everyone. So today we're going to do the Physics 111 Common Exam review. And here I have version A, okay, of the Physics 111 practice exams that you can find on NJIT. So I'm going to go ahead and show you how to do 18 questions, 18 multiple choice questions. And I'll show you, a few ways, different ways to do it. So let's go ahead and do number one. Okay, so for number one, it says that a student is driving a car, okay, at 60 miles per hour, okay, 60 miles per hour. Okay, so imagine that there is a car, this is a bad drawing, and then it's going at 60 miles per hour. Okay, and then they're asking us what is the speed in meters per second, right? We're giving it this in miles per hour, but we could find it, okay, in meters per second. And they tell us that, okay, there are 3.28 feet in 1 meter, and that there are 5,280 feet in 1 mile. Okay, but I did it a little bit different. I said that in 1 mile, you could do it in different ways. So you could also say that in 1 mile there are 1,610 meters, right? So that's basically 1.61 kilometers. So we can use that, and we can also say that there is, of course, 60 minutes in 1 hour and 60 seconds in 1 minute. So we're going to use those proportions. So we can go ahead and start by, okay, the given, which is 60 miles per hour, right? So we write down the units, so we're able to cancel them out later. And we know that in 1 mile there are, okay, 1,610 meters, right? So we're going to multiply that by that in the top or in the bottom? We're going to multiply by 1 mile, right? So 1 mile on the bottom so that this unit cancels out. And on the top we're going to put 1,610 meters, okay? Now we have to get rid of the hours. We know that in 1 hour there are 60 minutes, right? So we're going to go from hours to minutes, and from minutes to seconds. Okay, so we have to put it on top so that we cancel out the hour. We have 1 hour, right, per 60 minutes. And we have how many minutes in how many seconds in 1 minute? That's going to be 60 seconds again. So we have to cancel out the minutes, 1 minute over 60 seconds. See, these units cancel out, this cancels out, and we're left with meters per second. Now, once you plug this into your calculator, okay, so go ahead and plug it in your calculator. You're gonna get about 26.833 meters per second, okay? And you round it to two significant figures, so you're gonna get 27 meters per second. All right. In your answer choices, there was A, 2.24, B, 27, C, 134, D, 45, and E, 23. Okay, so you pick B. All right, so we're going to move on to any questions? You have any questions about this? Everything's clear. Okay, we're going to move on to question 2. How many million gallons of blood does a human heart pump in average in a lifetime? The average number of beats in a lifetime is about 3,000 million. 3,000 million beats. This is the average amount of beats in a lifetime. So in your lifetime, you might have, 3,000 million beats. Okay, so your heart might actually, do about. I mean, that's not. We're not going to try it out, unless you actually want to test that. But no. Anyways, and then we are told that the volume pumped with each beat is about 50 centimeters cubed. Okay, so per beat, we're going to have 50 centimeters of blood, 50 centimeters cubed of blood. Per beat. Okay, per beat, yeah. In a gallon, okay, so this is per beat, okay. And now this is, we're told that a gallon is 3,800 centimeters cubed, okay. And why do they tell us, the conversion factor for gallons to centimeter cube? Because we're asked to find how many million gallons, okay? But we have million beats, and we have this conversion factor, okay? So what are we going to go ahead and do? Okay, we're going to start with the given, right? So we're going to start with 3,000, okay, million bits. Million bits, okay? And then we have to find, okay, we have to find the conversion factor, right? So we have to use the conversion factor over here. So we're going to find, so we're going to have the millions in gallons, right? So what do we have to multiply this by? Okay, so we're given this. Okay, but this is 3,000, okay, million bits in a lifetime, and we want to find how much in volume this is, right? So we have to multiply it by, okay, multiply it by 50 centimeters cubed, because that's how much, okay, you are getting per volume, right? Per bead you're getting 15 centimeters cubed. So that's going to be times 50 centimeters cubed, because this is what your heart pumps,
Over 1 bead.
right, per bead. Over 1 bead, yeah, so 1 bead. Because this will cancel out. See? Now we want to find million gallons, right? So what do you have to do here?
Times 1 gallon over 30.
Times 1 gallon
Over 3,800.
over 3,800 centimeters cubed. And that cancels out over there. You see? Very good. And now when you multiply all of this, okay, 3,000 times 50 divided by 3,800, you're going to get, okay, you're going to get about 39.47. And of course, the units are going to be million gallons, okay? So that's going to be million gallons. All right, and then we're going to round this to two significant figures. You're going to see that in your answer choices, you're going to find something very close to that. So even if the significant figures is not, like correct, you're gonna figure it out easily. So if we round it to 2, that's going to be 39 million gallons. Okay. Nice. So we're going to move on to question 3. You have any questions? Okay. Now we're doing some physics. Okay. So now we're doing physics. All right. So a car A. Okay. Let me make a little drawing here. A car A. Okay. Starts 10 meters ahead of car B. So this is car B. Okay. Let's call this car B, and then this is going to be car A. Okay? They tell us that car A starts 10 meters ahead of car B. So if we say that this is 0, okay, 0 meters, this over here will be 10 meters, right? Okay? Now, car A moves at VA, okay, at a velocity function that is given as, okay, given as 3j hat plus 0, 3I hat plus 0j hat. And well, I mean, this is just the components of some vector that is in the x direction, because there's no, the magnitude of the y direction is going to be 0. So if we find the magnitude of this component, that's just the square root of 3 squared, which is just 3 meters per second. Okay? Now we're going to find the magnitude of the velocity of car B. Now for car B, we have 7I hat, okay, plus 0j hat. And the same, we do the same thing, because over here we have 0 for j hat component. So that's going to be square root of 7 squared, which is just 7 meters per second. Okay, this is for car A, this is for the velocity of car A, and this is for the velocity of car B. Okay, so we have 3 meters per second and 7 meters per second. Now here is the thing. We're asked, okay, how many seconds does it take car B, okay, this car, to catch up in position? When they say to catch up, they mean like when is the position the same. So this car has to catch up with this car. Okay. Now there are two approaches to do this. You can either just like straight up put the the second kinematics equation, or you could do it the calculus approach, right? Because you have two velocity functions over here. So you know that the velocity function, okay, the velocity function, when you take the integral of the velocity function, okay, with respect to time, you're going to get your position function, right? Did you learn that, or maybe? Right. So like the integral with respect to time of v is going to be x. Did you learn that, or they didn't tell you that? They did?
Is that like the derivatives for like motion velocity, time to velocity acceleration?
Yeah,
Oh,
because the derivative of position is velocity. The derivative of velocity is acceleration. And if you take the integral from acceleration, you're going to go backwards, because the fundamental theorem of calculus. So if you take the derivative and the integral is like inverse.
Going back.
Yeah, so it's like adding and subtracting pretty much, or multiplying and dividing. They're inverse. Okay? So what we want to do is we want to set both of these the position functions equal to each other. And I mean, we all know the kinematics equations, but if you don't know it, you can derive it using calculus. You know that's going to be, okay, let's take the integral of both velocities and see what the position functions are, right? So let's say we find these, the position function for A. So that's going to be integral of VA, right, dt, which is going to be integral of 3 dt, which is just 3t, plus some initial value of position. And that's our position function in terms of time. Okay? This is because when you integrate, when you take an indefinite integral, you have a arbitrary constant of integration. That's what we call it. Now, if we take the integral of v dt, that's going to be 7t plus x0 equals to xt.
So when you take an integral, you add a variable and you add the initial.
You add the initial value, yeah, pretty much. So when you integrate, so let me put it over here. When you integrate x to the power of n dt, I mean dx, because we're integrating in terms of a variable x, you have to, this is the boundary here, okay. You have to add 1 to the exponent. So that's going to be n plus 1, right? So that's going to be n plus 1, so n plus 1. And then you divide it by the exponent that results from it, yeah. And you have to add a constant of integration, c. Okay, but because why am I adding, okay, x0? That's because we're taking the integral of the velocity function, which is going to get us the position function. And so the initial position, we can just denote it as x0 instead of just writing c. Okay. Now, what are we told about the initial position of car B? It's 0, right? So x0, xb0, okay, this is xa0, and this is xb0. xb0 is 0. And what about xa0? What is the initial position of A? It's 10 meters. So we can rewrite this as, okay, the position function of A in terms of t is equal to, okay, 3t plus 10, right? And the position function of B is going to be 7t.
And then do you set these equal to each other?
Right, because these are the position functions. So we want to find out when these two catch up, right? When B catches up with A. So if we do 3t plus 10 is equal to 7t, okay? We just solve this equation over here. So this is going to be t is equal to 5 over 2, okay? 5 over 2, which is 2.5 seconds. Or you could do it the easier way. This is just to show you like why you know the kinematics equation work the way they do. It's because you know the second kinematics equation is delta x, right, equals v0t plus 1/2 at squared, right? But we don't have acceleration in the x direction, right? So we're just left with this, okay? And then we know that delta x is x final minus x0. If we bring x0 to the other side, we have v0t plus x0. So this is where that x0 comes from. It's a constant of integration. All right?
I have a question.
Yeah, question?
So for the changing x equals VOT, so changing x to be 10, VO would be 3, right? Because we're talking about car A.
VO? Yes.
Okay.
Yeah, absolutely. Yeah, if they give you the acceleration, okay, v0 for each of these is going to be respective. Okay, this will be 7 for B, and then this will be 3 for A, 3 meters per second. Okay? But yeah, if you want to do it quickly, if you're doing the exam, do the second kinematics equation. So all you have to do is just plug in the values, okay, and then set it equal to each other. Now for question 4, we have an airplane, okay, accelerates with 7.33 I hat meters per second, and from an initial velocity of 200 I hat meters per second for a distance of 1.20 kilometers. Okay, so we have, I make another drawing. So we have a plane over here, right? And then we're told that the acceleration of the plane, okay, is going to be equal to, okay, they show it in vector form. So it's going to be 7.33 I hat plus 0 j hat, which is just basically that, right? So you don't even have to write that, but that's just like conceptual. So you don't have to, okay? So you just find the magnitude of this. If you find the magnitude of this, that's just square root of 7.33 squared, and that's just 7.33 meters per second squared. That's the acceleration of the plane in the positive x direction. And the initial velocity, v0, Okay, it's given in component form, but you already know how to, okay, convert that, okay, into the magnitude. So that's going to be 200 meters per second. And it's going to travel for a distance of 1.2 kilometers. And they ask us, what is the final velocity? So what's B final? So we're given acceleration, we're given initial velocity, and we're given delta x. This is delta x, the change in position, right? So what does this sound like? It sounds like one of the kinematics equation, right? It cannot be the first one, right? The first one is V final equals V0 plus AT, but we don't have time. So we have to, maybe the second kinematics equation, delta x equals V0t. Oh, we have t again, right? Plus 1/2 AT squared, so that doesn't help us either. And the third one, of course, is V final squared equals V0 squared, right? Plus 2a delta x. And look at that. We don't have time, so we don't have to worry about that. We have acceleration, we have the change in position, and we have the initial velocity. Sweet and simple, right? So all we have to do over here, first solve symbolically, right? So we're going to take the square root on both sides to find the final velocity. So that will be the square root of V0 squared plus 2a delta x. And now you can plug in, okay, your values. Never plug in your values in the middle. Otherwise, you're going to get lost. And if you make a mistake, it will be easier to check your mistakes symbolically than numerically. So that's going to be the square root of the initial velocity, which was what, 200 meters per second? Squared, right? Plus 2 times the acceleration, which is 7.33. And then multiply by the change in distance, 1.2 kilometers. And all the units are in, okay, they're all in metric system, so those are the right units. KMS units, I think is what they call it. Okay, so that if you plug it into the calculator, that should give you, first is 239, okay, 0.98 meters per second for the final velocity. But you're given 3 sig figs, so you could round it to 3 sig figs, and you're going to get 240 meters per second. So that'll be the final velocity. All right. All right. A car drives carrying a flag of width, okay, W equals 0.5 meters. So there's pretty much, okay, there's a car, and then the car carries a flag, and the flag has a width of 0.5 meters. Okay, this over here, this is delta x. It's 0.5 meters, okay? Now, they tell us that the flag goes through a photogate. So a photogate is something that measures, okay, position, right? So it basically shoots a beam of light, and it detects when the beam of light is going to be, okay, passed by. So they ask us, okay, if the average speed of the car, is 20 meters per second, okay, what is the photogate time interval in seconds? Okay, so what do we have to use here? So what are they trying to ask us? They're trying to ask us, what is the time interval, okay, from when the flag starts to, okay, touch the beam of light until when it leaves, okay, the flag. So when the beam of light touches the flag until it leaves, that's delta t. And also we have delta x, right? We have the average velocity for that given time interval, okay? So we could try, okay, how about the first kinematics equation, right? Maybe? No, because first kinematics equation, right, it doesn't have distance, right? So that doesn't help us. But what about the second kinematics equation, right? So delta x is equal to B0t plus 1/2 AT squared. That definitely works, right? Because we don't have acceleration, do we? But we do have the initial velocity, or the average velocity, and we want to find time. And we definitely have delta x, right? So let's solve for time, because we want to find the time interval. So delta t is going to be delta x over v0, or the average acceleration. And that's going to be, okay, you just plug in your values, 0.5 over 20 meters per second, right? And that's basically 1/2, right, over 20, and that's 1 over 40, or 0.025 seconds. Okay? Got it. Questions? Clear. Now a jet test pilot can accelerate at 5G. Okay, 5G. So let me make a little drawing over here of a pseudo jet. All right. So this can accelerate at 5G. Okay, 5G, which is basically 5 times 9.8 meters per second, right? Squared. Okay, so it can accelerate at 5G. Now they tell us that at the acceleration, at that acceleration, she will black out in 5 seconds. So at t equals 5 seconds, when it starts accelerating at this acceleration, she's going to black out, right? Now she plans to start from rest and to a speed of up to Mach 3. So Mach 3 is going to be 3 times 331 meters per second. That's going to be Mach 3. And then they ask us, how long in seconds, will this part of her planned flight take, if she can do it? Okay, so we're asked to find time. But we're given acceleration, we're given time as well.
What is that second one? Is that
This one?
not the second?
Oh, the second one? Here? Oh, this is 5. Looks like 5 seconds.
Oh, 5 seconds.
Yeah.
So they give us time.
Yeah, they tell you that this is the maximum time. This is the maximum time, right? When she's going to black out. But then they're asking us, how long, will this part of her planned flight take? So how long will that take? So we can certainly use the first kinematics equation here. So let's see. We have B final, right? Do we have B final? We don't have B final. Well, we have that, the acceleration is 5G. And we know that if she reaches a speed of Mach 3, she will black out in 5 seconds, right? So let me read the question to you again because it's kind of wordy. A jet test pilot can accelerate at 5G, right? At that acceleration, she will black out in 5 seconds. She plans to start from rest. From rest means that V0 is 0. And she will speed up to Mach 3, but that means that will be B final. So how long will this take? So we use the first kinematics equation, so that'll be V final equals V0 plus AT. We know that's 0, and we just want to find T, right? So T is going to be, Mach 3, so 3 times 331 meters per second, divided by 5 times 9.8 meters per second squared. And that should give you the time. So that's going to be 20 seconds. All right? Got it? A military jet, all right, they like a lot of army stuff. All right, military jet first flies in one direction, turns sharply, and then flies in another direction. As described by the vectors, A is equal to 2j plus 4j, and then B is equal to 5j plus minus 3j. So this is, I'm sorry, this is 2I. Yeah, I keep confusing those. That's I and that's j. Okay. Now, take the x-axis as east and find the angle in degrees of the sum of these motions relative to the east. Okay, so we have something like this. So we have coordinate plane, right? This is 0, 0. This is I and this is j. Okay, so if we graph the components of vector A, so that's 2I, that's 2 to the right. So 1, 2, and 4j up. So 1, 2, 3, and 4. So that's going to be something like that. That's vector A. Okay. For vector B, we have 5I, so that's going to be 1, 2, 3, 4, 5, and 3j below, right? So 3j down, 1, 2, 3. So that should be something like that. Okay? And we're asked to find the angle between them, right? Oh, the sum of the vectors, and then the angle, okay?
Find the resulting vector?
Right, we have to find the resulting vector, and then we're going to find the angle that it makes with the x-axis. Okay? So we're going to go ahead and do that. So if we add these vectors, it's going to be something like that, right? And then the resulting vector using the tip to tail method will be something like this, right? But of course we can, okay, we can just add the components, right, of the vector.
How are you going to do that?
What's that?
You weren't going to add the components?
Yeah, you can just add the components, of course, yeah. So you're gonna get that the sum of vector A plus vector B is equal to the x components, okay, added together. So that's going to be 2 plus 5 I hat, and then we're going to have plus 4 minus 3, which is 1, so 1 j. That's going to be the resulting vector, 7 I hat plus j hat. Okay, that's going to be the resulting vector. So it kind of looks like it. Look, 1, 2, 3, 4, 5, 6, and 7, and this is 1. And we just have to find theta. We know that this is a distance of 1, and this is 7. The x is 7. So we just have to find the angle. We have opposite and we have adjacent. Sounds like tangent, right? So we have tangent of theta. That's going to be equal to 1 over 7, right? Opposite over adjacent. And so theta is tangent inverse of 1 over 7. And that should be about 8.1 degrees. If you round it up to 1, that's going to be 8 degrees to one significant figure. Okay, any questions about that? So we have a car slows down because of traffic, and it has an acceleration of negative 1 meters per second squared. After moving for 6 meters, it has a velocity of 4 meters per second. So we have a car, okay, again, better design, okay. So this is going to be accelerating, okay, negative 1 meters per second squared, right? And then we have that the final velocity, so B final, okay, B final is equal to 4 meters per second. We don't know what's V0. And we know that delta x, okay, the distance it travels, is going to be 6 meters. Okay, so we just have to use one of the kinematics equations. So which kinematics equation does this sound like? We have acceleration, we have delta x, and we have V final. Third kinematics equation. Yeah, so let's use V final squared equals V0 squared plus 2 delta x a. We solve for the initial velocity, so we're going to have that V0 squared is equal to V final squared minus 2a delta x, and then we just take the square root on both sides. So we have that it's going to be the square root of V final squared minus 2a delta x. Okay, then you plug in your values. So that's going to be the square root of B final squared, which is 4 times 4, 16, minus 2 times negative 1 times 6. That's going to be 12, because this is negative times negative is positive. Yeah, good one. So 16 plus 12 is going to be what? So that's going to be equal to, okay, the square root of 28, right? And that's about 5.3 meters per second. Good catch. We have that a car drives off a cliff next to a river at a speed of 30 meters per second, okay? And it lands on the bank of the other side. Okay, so that's going to be something like that. This is the river, this is the other side, and the car is over here. So it has a speed of 30 meters per second, okay? But it's, of course, it's parallel to the ground, right? So that means it's only in the x direction, right? It doesn't have a y component. Now, we're told that the road above the cliff is horizontal, right? And 8.3 meters above the other shore where the car lands, right? So that's going to be delta y equals 8.3 meters. Okay? Now, we're asked that the tires, okay, on the car all hit at once. Air resistance and friction are negligible. So how long in the air, okay? How long is the car in the air? That's the question. Okay, so well, we're given the x component of the acceleration, but that's just like a extra information, because we're only asked to find what's the time when this is on the air, right? So it doesn't really matter if it's going at the speed of light. It could go at the speed of light and still be the same time. Okay. So let's find what's the equation. Okay, the kinematics equation that we're going to use for this. We have delta y. We know that the acceleration that's always going downwards is, of course, g, right? That's g, negative 9.8 meters per second squared. And what else do we know? We know v0 for the y component, right? v0x is 30 meters per second. But what's v0y? That's 0 meters per second. So we can use second kinematics equation, okay? Because that's the one equation that has time. So that's going to be delta y equals to v0yt plus 1/2 gt squared. Okay? And we know delta y, we know v0y, that's going to 0. We don't know t. So we want to find t. So t is going to be equal to, okay, 2 times delta y divided by g, and then take the square root of that. Now, be careful with the negatives. y0 over here, y0 is 8.3, and y final is 0. So delta y is y final minus y0. So delta y is actually negative. Okay, delta y is actually negative. If we say that this is y0, okay? If we say that this is y0, well, it will be a different story. The car will be here and then, you know, up there.
If that was y0.
Yeah. Yeah, if this was y0, then of course it will be positive, but it wouldn't make sense because the car doesn't start here. The car starts over here. Okay? So if we plug that in, we have the square root of 2 times negative 8.3, right? Divided by negative 9.8. And the negatives cancel. So the time it takes should be, okay, 1.3 seconds. Okay, if you plug it into your calculator. Oh, this is a fun one. Okay, so the launch angle of a projectile is 30 degrees. Okay, so 30 degrees with respect to the horizontal. Theta equals 30. Okay, and its velocity in the x direction. Okay, so Vx is equal to 1.7. So it says this is only after 2 seconds. So this is not v0 x. This is Vx equals 1.7 meters per second at t equals 2 seconds. Neglecting friction, what is the initial magnitude of the projectile's velocity along its firing direction? Okay, so we're going to find v, pretty much, v0, the magnitude of the vector, v0. But to do that, we need to find the component in the y direction, which we don't know. So if we split this into 2 components, we have v0y, and we have, okay, v0x, which is what in this case? 1.7. They tell us that, okay, this is the velocity at 2 seconds. But what's the catch here? It doesn't matter if it's at t equals 1, t equals 3, t equals 5. It doesn't matter because the x component of the velocity never changes until, okay, it stops. So the x component is not changed. There's no acceleration in the x direction. So this is going to be 1.7 meters per second. And look at that. We have everything we need to find v0 because the magnitude of the vector v, okay, if we find the x component, okay, so v0x is equal to v0 times, okay, if we're trying to find x, this is going to be adjacent, okay, over hypotenuse. So that's cosine of the angle theta. Okay, we know the magnitude of v0x and we know cosine theta. So v0 is equal to v0x over cosine theta, which is just 1.7 over cosine of 30, which is just 1.7 over, okay, cosine of 30 is the square root of 3 over 2, right? 1.9, like I said, so that's going to be 2, if you round it to 1/6. 2 meters per second. All right, so for question 11, we have a rocket launching vehicle is moving forward at a constant velocity of 5 meters per second. So we have, okay, a rocket launching vehicle and it's moving forward at 5 meters per second. So this looks like a Soviet Katyusha. It's basically, you know, a rocket launcher. So basically, a cannon, okay, on the vehicle, so one cannon over here shoots a shell straight up, okay, with a velocity of 20 meters per second. So the shell is going to be going straight up at 20 meters per second. Okay? So that tells us that's the y component of the velocity. The shell moves without friction, okay, no air resistance. Okay, so that's negligible. And how high, okay, does the shell go in meters? So we're told that this is the x component of the velocity, right? So we can say v0x is equal to 5 meters per second, and v0y is equal to 20 meters per second. But guess what? v0x is irrelevant. We're not going to use it for our calculations because we're just going to find the time the shell is in the air, right?
Is it shooting straight up? Or
Yeah, it is. This over here is shooting straight up. Yeah, this is just a fancy drawing, but of course it's straight up. So there you go. So we're asked to find like what's the maximum height. So we have to account for some things here. So let's just make a miniature drawing over here of the car. So the shell goes like this, right? And it's going to go like that. At some point, that's the maximum height. And then it's going to come back down, right? So we want to find what's delta y. Okay? We know y0 is equal to 0. We want to find y final. All right? Now, this is, a projectile motion problem. So what do we know about the velocity, okay, at the apex? This is called the apex. What do we know about the y velocity at the apex? We don't know anything.
0.
Well, that's the y velocity, right? Is it 0 or is it x?
Wait, isn't it?
Yeah, you're right. It's 0. Yeah, the velocity, the y velocity is 0. Yeah, the x velocity is the one that doesn't change, regardless, because there's no acceleration, right? So ax is equal to 0, but of course ay is g, okay, negative 9.8 meters per second. Okay, so we know that v final will be 0 meters per second. And we have b0, which is 20 meters per second in the y direction. So we have b final, b0, we have g. We need what? We need time, right? Because we're trying to find how high it goes, but we don't know the time. We could do that, but there is an easier way to do this.
wait,
Okay.
final velocity is 0 because it's hitting the ground?
No, because we're trying to find the maximum height. So bx has a magnitude, right? b0x is this is the magnitude,
So
but by is 0.
so VF0 is also AX. Yeah, it's the same thing.
va0.
VFY
Oh,
is
bf.
also AX.
No, bfy is the y component. It's 0 for okay at this point. At this point we don't know what's bfy. Okay, but at this point bfy is 0. Vx is always 5 meters per second because the shell will move 5 meters per second until it comes back down. So, well, let's see. We have b final equals b0 plus at. We have time. We don't know time. I mean, we could kind of find time based on this, but I think we could use another equation. Let's try the third kinematics. B final squared equals b0 squared plus 2a delta y. And immediately we have delta y in that equation. We don't have time. We don't have to worry about time. But we do have acceleration. We have b0 and we have b final. So we have to solve for delta y because we want to find what's the maximum height. So we're going to solve for delta y. So that's going to be delta y is equal to bf squared minus b0 squared divided by 2 times a. A is g. Okay, we just substitute the values. Bf final is 0, and then we have b0 squared, right? So in this case, that's going to be what? That's going to be the y direction, right? So the initial y velocity, which is 20. Yeah, 20 squared, which is of course 400. Yeah, over 2 times negative 9.8. The negatives cancel. So that's like 400, right? Divided by, if I approximate this to 10, that's 20. So that's going to be 20 meters per second, approximately, right? You can use 10 for like free response questions because they're going to take points off. So I always use 9.8. But of course, if you approximate it to 10, there's no issue. You still get the same answer. It's actually the answer choice. So, yeah. All right. Any questions about that?
So it was asking for the velocity at the highest point?
It was asking for the maximum height. Yeah, because, I'm sorry. Yeah, you're right. Thanks for the question. It's actually in meters, 20 meters.
Okay.
Yeah, because we're asked for delta y. Yeah.
Oh,
not the velocity, because we know the velocity will be just the velocity, right? The x component of the initial velocity. So let's go to question 11. Okay, so a second launching vehicle is moving forward at 5 meters per second, and its cannon shoots a shell straight up. The shell moves through the air without friction for 2 seconds. How far in meters in front of the cannon does the shell land? Okay, so this is a trick question. Think about it. I'm going to read it to you again. A second launching vehicle is moving forward at 5 meters per second. So it's basically the same thing. Okay? The launching vehicle, it moves at 5 meters per second. Right? And then it shoots a shell again, straight up. Okay? At some speed. It doesn't matter what speed it is. It could be 20 meters per second. It doesn't really matter. And you're going to see why. Now, it moves through, okay, the ground, okay, for 2 seconds. So suppose this is t0, okay, equals 0, and t equals 2 seconds. So you're going to have, okay, a future picture of the truck over here. So you're going to have the shell, okay, the shell is going to travel at 5 meters per second in the x direction, just as the car is traveling 5 meters per second in the x direction. So what's going to happen is the shell is going to fall back down to the car and, of course, blow up or something. So, yeah, basically, what is going to be the what's going to be the delta x? Okay, so what's going to be the difference in distance between the shell's position and the car's position? Is 0. There's going to be no difference in position. They both end up at the same position. Okay, so because
So the time doesn't matter to you?
yeah, time doesn't really matter. And if you want to show that mathematically, okay, so we just use second kinematics equation. So x car is equal to v0 times t, right? I mean, we could use time to show like that's what happened. And then the x of the shell, okay, the position of the shell is equal to v0 t as well. Now look at that. v0 is the same for both of them, v0x. So that's just 5 times 2 equals 10 meters. 5 times 2 equals 10 meters. The position of both are the same at t equals 2 seconds, which means, okay, the shell lands on the car after 2 seconds. If the car keeps the same velocity. If the car were to accelerate, well, it would save itself from the explosion. But in this case, that didn't happen. Okay, so let's move on to question 13. This is a quarterback. So a quarterback launches, okay, quarterback throws a football at a speed of 32.1 meters per second. Okay, that's the magnitude of the velocity at that angle. The angle is 41.2 meters. I mean 41.2 degrees. That's the angle with respect to the horizontal. Okay. Now, what horizontal distance in meters can he throw it downfield if wind and air resistance are negligible or insignificant? So they're not telling us specifically that the ball is going to hit the ground. They're just telling us that, you know, he's going to throw the ball, and we're just going to find the distance, okay, the distance in meters from here to whenever it reaches the same position, the same y position. So we can take advantage of symmetry and suppose that this is the path that the football takes. So we're going to find this distance, okay, this distance over here, this delta x. We know that the velocity over here is what? The magnitude of the velocity. If the magnitude of the velocity, v0 over here is 32.1 meters per second, the velocity over here will be the same because of symmetry. So v final is 32.1 meters per second. The magnitude, right? We're not asked for the direction. Well, we know the direction. That's 41.2 degrees, right? Now, here is the thing. We have to, okay, find the x component of the velocity, right? We don't care about the y component, do we? And then which kinematics equation can we possibly use here? Because we want to find delta x, right? So we know first kinematics equation is v final is equal to, you know, v0 plus at. It doesn't have delta x. What about the second kinematics equation? Second does have delta x. What about the third one? It also has delta x, right? Now, the thing here is that this doesn't have acceleration. So if we use the third kinematics equation, that term cancels out, and that's like b final squared equals v0 squared plus 2a delta x, and delta x cancels out with a because a is 0, so that term cancels out. So we have to use the second kinematics equation. So x, is delta x is equal to b0t plus 1/2 at squared and a 0, so we don't write that. So delta x is b0t. Now, but this is the x component of the velocity, of the initial velocity. What's the x component of the initial velocity? So we have a triangle like that, right? This is 32.1, and this is 41.2 degrees. The x component goes like this, right? So we have to do that. We have to say that b0x is equal to 32.1 meters per second, right? Times cosine of the angle.
So it's cosine when you're trying to find x.
What's that?
You use cosine when you want to find x.
Yeah, but do you know why?
Because I just related to x is cosine, y is sine.
But don't do that, because then you're gonna get confused later on when it's actually the opposite. Sometimes it's the opposite, sometimes it's like that. But the reason for that is because look at this. Okay, we have a triangle, right? 32.1. It's a right triangle, right? This is the magnitude of the velocity. This is v0y, right? And this is v0x.
Oh, because it's opposite of the hypotenuse.
Yeah. So look at this. This is the angle theta, which is 41.2. To find what is sine of theta, that's opposite over hypotenuse, right? But we're going to have the v0y in there. To find v0x, we can do cosine of the angle is adjacent over hypotenuse. So cosine of 41.2 is equal to adjacent, which is v0x, over the hypotenuse, which is 32.1. We multiply this on both sides, and we get this. So that's why that happens. Okay. Now, if we find the magnitude of the velocity, that's going to be about 32.15 meters per second in the x direction. But we're asked for delta x. We're asked for the distance it travels in the air. Now, what do we need to know here? Okay, we need to know the time, don't we? Right? What do you think? What can we do here?
So that was only for velocity x.
Yeah, this is the x direction. Okay, the x direction of the velocity. And okay, we know that delta x is equal to b0t, but we don't know the time. So why did we find the time? We could find the time, but we don't know delta x either. So what can we possibly do? Maybe the third kinematics equation? No, that's not going to help us, right?
Yeah, because isn't that just vx squared minus v squared?
Yeah, that's just b final squared equals v0 squared plus 2a delta x. So we have to use something else here. How do we know the time? We don't know the time. If we knew the time, we could find delta x easily. We know the first kinematics equation, right? But it doesn't work for the x direction. But it works for what? What does it work for? Because the acceleration, the x acceleration is equal to 0. But what is the y acceleration? So that's g, which is negative 9.8, right? Meters per second squared. Look at that. Yeah, we could use the first kinematics equation. We already know the initial velocity, right? And we already know the final velocity. Okay? So, okay, let's use that. So we're going to find t. T is equal to v final, okay, minus v0 divided by g, right? Now, what's v0? v0 is 31. We're trying to do this in what dimension? The x or the y dimension? Yeah, so that's v final y and v0 y. So we already know the x component of the velocity, but we don't know the y component. So we have to find the y component doing the same process. So v0 y is equal to 32.1, right, times sine of the angle, 41.2 degrees. Okay? And then we can plug that back into that equation over here. Now, what's the final velocity? We said that the final velocity was the same, right? So, but here's the difference. This is 32.1. This is the y component, and this is the x component. The x component doesn't change, right? It's the same, it's positive, same magnitude, right? But what about the y component? It changed what? Direction. So this is positive, this is negative. So v final is negative. So that's going to be negative the y direction, the velocity in the y direction, which is going to be 32.1 times sine of 41.2. And we're going to subtract that by the same thing, 32.1 times sine of 41. All of that divided by g, which is what? Negative 9.8. Take a seat, man. See? And look at that. What happens when you add two things that are the same? That's just basically 2 times that, right? And the negatives cancel out. So we have that t is equal to 2 times 32.1 sine of 41.2 degrees divided by 9.8. And then you plug that into your calculator, and you should get some number, and that's going to be 4.31 seconds. That's the time. But we're not looking for the time. We're looking for delta x, right? Question?
Yeah, but how do you know that VF is 32.1? Like, how do you know the initial velocity?
Oh, we're told that v0 in this direction is 32.1 meters per second.
But how do we know VF is 32.1?
Bx?
You said to think
The
of it
VF.
like symmetry.
Oh, okay.
Oh, how do we know that the final velocity is 32.1? Yeah, because basically, because of symmetry, the velocity at this point is the same as the velocity at this point. The velocity at this point is the same as the velocity at this point, and so on. It's like a parabola, right? So if you have, for example, right, this is 2, so that's basically negative x squared plus 2. What is the, let's say we have negative 1 and we have 1, right? So what is the value, okay, the value of y over here if we plug in 1? That's going to be 1, right? What is value if we plug negative 1? It's going to be 1, right? It's the same. So that's why we're taking advantage of symmetry, right? So we know the time, and finally we can use it in this equation. So we know that delta x will be equal to v0x, which in this case is this over here. So 32.1 times cosine of the angle, which is 41.2 degrees. And we're going to multiply by the time we found, which is 4.31 seconds. And then if you plug that into your calculator, okay, you should get 104 meters. So that's the distance that the ball travels. This one was a little tricky. I actually got it wrong the first time I tried it, because I forgot to multiply this by 2. So I said, well, the initial velocity equals to the final velocity, but I forgot that the y component, okay, I dismissed that the y component changes direction. So here is negative, here is positive. So that's why, okay? And at the end, the negatives cancel out.
For the time, why did we do the velocity final and initial of y? Like, why did we do that?
Good question, yeah, because what if we use this for x?
Yeah.
Bye. What if we use this for x? Oh, did you forget something? Yeah, pick it up. Yeah, that's all right. Don't worry. I'll just cut this part. I'll just cut it. Don't worry, Dad. Yeah, those are mine.
All these?
Are these yours?
What's that? Yeah, only the top one, the black one.
That's
Yeah. That's your folder?
I can get it.
No, that's okay. Yeah,
Appreciate it.
no problem. All right. So you're not going to stay, Brian?
I gotta go to Walmart.
That's okay. I get it. I'll post the video anyways if you want to see it later.
Watch it.
Sure.
Well, I need
Some questions.
magnetism, okay.
Magnetism?
Yeah.
I'm going to do it later, yeah, after this, right after this. All right. So, yeah, the answer is 104 meters.
Okay.
Okay, now let's move on to question 14. This was 13.
Oh wait, but I had asked why we use
Yeah.
F.
Oh, you're right. Yeah, let me answer that question real quick. Let me just erase this. Because what if we use the first kinematics equation? We used first kinematics equation to find time, right? In the y direction. Why not in the x direction? Well, look at this. If we have v final x equals to v0x plus axt, what is ax? 0. So we don't know what's time if x is 0. We just know that the initial velocity in the x direction equals to the final velocity in the x direction.
But why like?
No, yeah, keep asking questions.
Okay.
That's okay.
Even if it does equal 0, but like that's what it is. So like why wouldn't it be 0? You know?
No, that is not equal to 0. This equals 0. But because they are being multiplied by each other, the product will be 0. 0 times anything is 0. T could be a million,
So-
but it's still 0 because
But
a
if
is 0.
it's the true acceleration, so it would.
Uh,
so if this
but that's-
is there, we just don't.
Look, this is the ball. Acceleration due to gravity goes down. What is the acceleration in the x direction? 0. There's nothing, right? So that's why we say ax is 0 and ay is negative 9.8 meters per second squared. So if we know one of the values for y, right, which is just negative 9.8, we plug it in.
We changed it to y because since it's not giving us t. So
Yeah.
we're like, okay.
Because we want to find t in order to find right, delta x equals v0x t, but we don't know t. However, we can find it using the y component because we know the velocity in the y direction, right? If we know the magnitude of the velocity. This is v0 sine theta, while this is v0 cosine theta.
Okay.
So this is v0 y. This is the y direction, the initial y velocity. So if we know that, we can use this in the y direction, and we know the acceleration in the y direction. But we don't know the time, so we can find time and plug that time back into this equation.
Okay. All right.
Got it? Any other questions? No? All right, let's move on to questions. A plane in level flight, okay, so it's not moving up and down, right? So it's something like that. Okay, so a plane in level flight, suppose it's a Japanese bombardier. Okay, so it is flying at 98 meters per second. That's the velocity. Oh my god. Okay, and the altitude, at that point is 985 meters. Okay, that's the altitude. And so the plane drops a package. Okay, the plane drops a package exactly at that point. It doesn't matter which point in time. And then the package, okay, is going to fall, right? So find the speed. Oh, I'm sorry, this is not 985. This is 935. Yeah. Okay, so find the speed in meters per second with which the package lands. Okay, suppose that the package, okay, starts to travel like that, right? So just as the plane moves, right? So what is the x component of the velocity of the package? 98. That's because it was moving at the same speed as the plane was, right? And that's the final velocity. So that's 98 meters per second. Okay. What do we know about the acceleration in any direction?
Oh, it's 9 point.
For the y, right? What about for x? 0. Good. So we know a is equal to g equal to negative 9.8 meters per second squared. Good. We know acceleration. We know velocity. We know delta y. But be careful with delta y. Y0 is this, right? Equals.
It's negative.
Yeah, it's negative because y0 is 935, right? Meters. and y final is 0. And delta y is y final minus y0, which is negative 935. So that's where the negative comes from. Okay? So what can we use? We know delta y, we know g, we know the velocity, but we need to find the magnitude of the velocity right before it touches the ground. So it's going to have a velocity like that. And we need to know the magnitude of that velocity right before it touches, right? So which
Third one?
third kinematics equation? It sounds like it, yeah, because if you think about it, well, let's see. B final squared equals to B0 squared, right? Plus 2/8 delta y in the y direction, right? We know B final. Well, we don't know B final, do we? But we do know B0, which is just 0, right? We know the acceleration. We know delta y. So why don't we just plug it in, right? But be careful. This is to find what? Which component? Y. Yeah. Good. So V final y is going to be equal to the square root of V0y squared plus 2g delta y. And then you can plug in your values. Don't forget delta y is negative 935. So B final y is equal to the square root of B0y, which is 0, right? Because right over here, the y velocity is 0, right? So that's going to be 2 times negative 9.8 meters per second, right? Multiplied by what? Negative 935. Negatives cancel out. That's a good thing. So B final y is equal to the square root of that, which is 135.37 meters per second. But this is the y velocity right before it touches. So we're going to have something like this. This is B final. We have the y component, which we found is 135.37. And we have the x component, which never changes unless, okay, it stops, which is 98, right?
Also, you just do Pythagoras.
Yeah, you could just do the Pythagorean theorem. So we can do B final is equal to the square root of 98 squared plus 135.37 squared. And that should give you the final velocity, the magnitude of the final velocity, which is 167 meters per second. So for question 15, a bin fills a volume of 3 millimeters cubed. To compare the size of the bin with a large container, what is the volume of the bin in units of meters cubed? So we have a bin, okay, and the size of it, okay, I mean not the size, the volume that it fills, right, is going to be 3.0 millimeters cubed, right? Now this is all cube. It's not. You have to be careful with that, right? Now we want to compare this to a large container. We want to compare it to a large container, okay? In units, okay, of meters cubed. So what do we need to know? We just need to convert this into meters cubed. Now this is the same as saying, okay, 3.0 times, okay, that in parentheses, very important. 10 to the power of milli means negative 3. So negative 3, okay, meters cubed. Now if we cube this, we just multiply this by that. So that should give us 3.0 times 10 to the negative 9 meters. So that should be the answer. That's D for this question. And if you want to be fancy, this is basically 3.0 nanometers. Yeah, 10 to the negative 9 means nano. Okay, so that's the answer for question 15. We have 3 more to go, 16, 17, and 18. We have a speeding car moving at a constant speed of 60 meters per second. So there is this highway, and then we have the speeding car, and then the velocity is 60 meters per second. And right over here, there is a cop. Okay? So there is a cop. and then the cop sees that the car is speeding, it's over the speed limit, right? So what does the cop do? Well, of course, he accelerates. He starts to accelerate at 2 meters per second squared, okay, to try to catch up to the speeding car and stop it. Now, how long in seconds will it take for the policeman to catch up with the car? Now, this is like one of those position problems, right? So I'm going to show it to you in two ways, two flavors. First, using just straight up two kinematics, second kinematics equation and calculus. So we can do it in two ways. So what do we know about the velocity, the initial velocity of the car, of the police car? Is 0, right? V0 is 0. What do we know about the acceleration? It's 2 meters per second squared. What do we know about the velocity, the initial velocity of this car? It's going to be, of course, 60 meters per second, right? And that's also V final. V final equals V0, okay? And it's 60 meters per second. The acceleration of this car is what? 0, yeah. It doesn't accelerate or it doesn't deaccelerate, so it's always the same velocity, okay? Now, of course, we can use second kinematics equation. Delta x is equal to v0 times t. Okay, we want to find the time in seconds when they catch up. Now this is, let's call this delta x car, and let's call this delta x police equals v0 t. Okay. Oh, and of course we have to consider, right, the acceleration component, right? Because we actually have acceleration for one of these. But which of them is the one that has acceleration? Police car, right? So the police car has acceleration. The car that's speeding, it doesn't have acceleration. So that term goes to 0. Okay? Now, we can set these two equal to each other to find when the position is the same. That means when the cop catches up with this car. So we have that V0 car, okay? Oh, and what's the initial velocity of the police? 0, right? So this term goes away. So V0 car, okay, we're going to set this equal to each other. So delta x car is equal to delta x police. Okay, so V0 car times t is equal to 1/2 AT squared. And we just have to, okay, bring this term to the other side. So we're going to have something like this, 1/2 AT squared, okay, minus V0 of the car times t equals 0. We factor out a t, see? We factor out a t. So we're going to get something like this, 1/2 a times t minus V0 of the car. And we know that t equals 0, and t is equal to V0 of the car divided by a, okay, and multiplied by 2, right? Does it make sense? So these are the two times when their position is the same. At t equals 0, the speeding car passes the police. And at t equals 2v0 car over a is when the police catches up with the speeding car, right? So what is the initial velocity of the car? We know it's 60 meters per second. It's always like that. And what is the acceleration of the police? It's 2 meters per second squared. So we do, look at that, 60 seconds. At 60 seconds, the cop catches up with the speeding car. And I'm going to show you the calculus way to do this. So look at this, which is basically the same. It's just that it's more it's more conceptual. So we have to sketch, okay, we have to write down the acceleration function of the police. We know that's going to be what? That's going to be 2 meters per second, right? 2 meters per second squared. The acceleration function of the car is 0. So we don't write it down because if we take an integral of 0, we're just going to get 0. But we do know the initial velocity. So v of t, the velocity function of the car, is going to be what? It's going to be 60 meters per second. Now we want to find delta x, okay, of car, and we want to equate it to delta x of the cop. So we have to take two integrals for this, and we have to take one integral for this, right, to go back to position. So let's do the acceleration of the cup. So integral of the acceleration function, dt, equals integral of 2 dt. So the integral of acceleration is b, velocity. That's going to be equal to 2 times t plus an initial velocity of the police, right, of the cup. And we know that's 0, because the initial velocity of the cup is 0. Now we take another integral, b of t, integral of b of t dt equals to integral of 2t dt. The integral of the velocity function is the position function, so this is going to become x car equals to, what's the integral of t dt? Integral of t dt, you add 1 to the exponent, 1 plus 1 is 2. You divide by that. So it's 2t squared over 2. This cancels out. See? Plus an initial position of the cup. And we're going to say that this position is 0. Okay? So this goes to 0. Now we know that the position of the car is equal to t squared. See? Okay? Now we're going to do the same thing for the oh, I'm sorry, this is supposed to be for the cup, right? Yeah, this is the cup. We're going to do the same thing for the car. So we know the velocity function of the car is bt equals 60. If we take an integral, okay, integral of 60 dt, integral of b dt, the integral of the velocity function is, okay, the position function, so x car, this time, yeah, is going to be equal to 60 times t. You see?
Yeah.
Plus an initial value of the position, which is 0. So look at that. We have x car and we have x cup. If we set it equal to each other, we know when it catches up and we can find the time. T squared equals 60t. You factor out a t and you get t minus 60 equals 0. So t equals 0 and t equals 60. So this is the calculus way to do it. It's a little longer though. So you might want to use the second kinematics equation.
But it makes sense though.
Yeah, this makes sense. So that's a good thing. Okay, moving on.
That's
Any
a
questions?
D, like,
Which one?
A D after the 2t,
Right here?
right above.
And the integral.
dt, yeah.
D, oh,
Yeah, that means differential t. Or integral of this with respect to t. Okay? Because you guys didn't start doing integrals yet, right? In Calc 1? Okay. Yeah, you're going to start like probably next month. You're going to start with the fundamental theorem of calculus, which is pretty easy. The fundamental theorem of calculus just says that the derivative of, okay, the integral is just the function, right? That's it.
Your data's about to die.
So we're going to do
17.
17, yeah. Now for question 17, okay, another car moving at a constant speed of 60 meters per second passes a policeman who starts his motorcycle from rest in 10 seconds and then accelerates at 2 meters per second. Okay, be careful with the word in there. How far in meters from the original point will it catch up with the car? So let's do the same thing. I erased it for no reason. Now I have to do it again. So we have the same situation, okay? Now in this case, we have the cop over here. Okay, the cop over here apparently slept for like 10 seconds. And so he didn't start his engine after 10 seconds. And the car, of course, is going to be farther away, okay? If it's moving at the same speed. Okay, 60 meters per second. Now, add t equals 10 seconds, right? The acceleration is equal to 2 meters per second squared. So that means that t equals 0, the acceleration, between t equals 0 and t equals 10, the acceleration is 0. The car, the cop didn't start his engine until like 10 seconds afterwards, right? And so we want to find how far in meters from the original point will it catch up with the car, right? So this is the original point, right? This is x0. So this car passes, okay, the car at x0. So that's the initial value of the position. So here's what we're going to do. We're going to do the same thing. We want to do, okay, x car is equal to x cop, and then find the time, right? But the position function is going to be a little different, okay? And you will see why. So first, let's focus on the position function for the police car. So how can we do that? So we have, if we use the second kinematics equation, right? So x cop is equal to, okay? So let's put it like x cop, which is x cop final minus x cop 0 is equal to, okay, b0t, right? Plus plus 1/2 at squared, okay? We know that the initial velocity is 0, right? And we know that at 10 seconds the velocity is, okay, 2 meters per second squared. So we're going to have something like this. X cop is equal to, okay, 1/2 at squared. But what about x car? Okay, what about x car? That's going to be a little bit different, right? We first need to find what's the initial position, because our time reference is going to be when t equals 0 for the cop, right? So essentially, what's going to happen is we're going to let this car, move for 10 seconds before this car starts, right? So we need to find the distance that this car travels from this point to whenever it's t equals 10 seconds. And that's going to be our initial position for this car. So let's do that. We know that x car, okay, is equal to v0 times t. We know the final. Do we know the final? No, we don't know the final. We want to find the final position, right? At t equals 10 seconds. We know the velocity, we know t, so x car is equal to 60 meters per second times 10 seconds. That's 600, okay, meters. So basically, this distance over here is 600 meters, okay, at t equals 10 seconds. But at this point, we're going to say, okay, now t equals 0 at this point, when the cop starts his engine and when the car has traveled 10 seconds. That's t equals 0 at this point, okay? So we're going to say that this is going to be the initial position, right? 600 meters with respect to this point. So we can say that x car, okay, is equal to, okay, v0 times t, right, plus x0 car. And we know x0 car is this, okay, 600 meters. Now what about x cop? It's just 1/2 at squared at t equals 0 in this new frame. Now let's set it equal to each other and see what happens. So 1/2 at squared is equal to v0t, okay, plus x0 car. Nice. We have a quadratic equation. Hopefully your calculators have that function, so you don't have to worry about it. So we just have to, okay, solve this quadratic equation. Okay, if you don't have a calculator that solves, okay, a quadratic equation, well, you have to use the quadratic formula. So let's just plug in the values already. We have 2 over 2 is 1. So that's t squared, right? Because the acceleration is 2, correct? Minus the initial velocity of the car, which is going to be 60 meters per second times t minus x0 car, which is 600 equals 0. Okay, you plug it into your calculator if you have the function. If you don't, you have to use the quadratic formula. So t is equal to negative of b, so positive 60 plus or minus the square root of 60 squared minus 4 times ac, so minus 4 times 600, negative 600. All of that divided by 2. Okay, you only take the positive value, okay, because we don't have negative time. You can travel backwards in time. So t is going to be, okay, t is going to be some number. I don't remember what it was when I put it here. Okay, but you're going to plug that number into, okay, the equation that will allow us to find the distance, okay? Because we're asked to find how far in meters, right, from the original point will it catch up with the car. Okay, so what's going to be t in this case? Oh, I got it. It's 68.7. Yeah, right? Let me know if that's correct. 68.7, 298 seconds. Is that it? Okay,
Yeah.
we agree. That's t in seconds. And we want to find how far, okay, in meters from the original point will it catch up with the car. So we're talking about the police car. So we can do one of the kinematics equation. We have time, we have delta. Well, we don't have delta x. We want to find delta x, right? Final delta x. We have the initial velocity. We have initial acceleration. So we just use the original function, right, of the police car, which is this. So we use x cop is equal to 1/2 at squared plus x cop 0, which is 600. So we just plug it in, right? So 1/2 times 2 times t, which is 68.7 squared plus 600. And that should give you, okay, that should give you about 4,700 meters. So at 4,700 meters, or 4.7 kilometers, this police car is going to catch up with the speeding car. Given that the police car forgot to start his engine right after the car passes the police car. So it took him 10 seconds, right, to start his engine, to start to accelerate at 2 meters per second. Okay, any questions? All good? All right, let's move on to question 18, the last one. A drone is in level flight at a speed of 201 meters per second. So there's a drone and it's in level flight, okay? So, and the horizontal speed is 201 meters per second, okay? And the altitude is 802 meters.
That's a nice drone.
Oh, thank you. So this is the altitude, right? Now, at what horizontal distance in meters from the target should the remote pilot drop an A package so it lands on the target? Suppose there is the target over here. See, the question is worded in a way that, you know, it's kind of like trick question, but because they don't really tell you, like, okay, assume that the package is dropped exactly at that point. And so, I mean, they don't specify where the target is, but that's what we want to find. We want to find the x direction, the x distance. So the distance, the displacement of the package from here to here, okay, so that it hits the target. All right, so he's going to drop a package at this point, right? And we want to find delta x. We have delta y. Delta y, remember, if this is y0, which is going to be 802, and y final is 0, so delta y is negative 802 meters, okay? Now v0 x, right, the initial x velocity is 201 meters per second. And we're asked to find, okay, at what horizontal distance, so we're going to find delta x so that the package lands on this target, okay? So what can we do here? We have delta y, we have v0x, we have, okay, g, of course, acceleration in the y direction is negative 9.8 meters per second squared. And of course, the acceleration in the x direction is 0. So we could find time, right? We could find the time it takes for this package to come to the ground. And then we can use an equation, the second kinematics equation for displacement, which is v0x times t, to find displacement. But we need t. So we gotta use the y components, right? Okay, the y components of acceleration and velocity to find time. So we can use the first kinematics equation. So v final y is equal to v0y, right, plus at. What's v0y? V final y after it lands on the ground? It's 0. What's b0y? Is it also 0? It's also 0, right? So that's not going to work out because this cannot be equal to 0. or at least we're not going to be able to do anything with it. So how about we try the second kinematics equation? So delta y, because we have delta y, right, is equal to b0y times t plus 1/2 at squared. We can certainly use that because we have delta y, we have b0y, right? That's 0. We have g. So look at that. That's it. T is equal to 2 times delta y divided by g, okay, and then square rooted. So that's 2 times negative 802 divided by negative 9.8, and then take the square root of that. That should be the time, and that is going to give you, okay, that's going to give you 12.8 seconds. Okay, so that's the time it takes for the package to go from, okay, this height to 0, independent of the x velocity, right, which is 201 meters per second. Okay. Now we plug it into here. Delta x equals v0 xt, because in this case, delta x is dependent, okay, on the x velocity. Here, delta y, I mean the time here, the time regardless, whatever it is independent of v0x. Delta x is dependent on v0x, so we're going to plug in delta x is equal to v0x is 201 meters per second, and then we have that it takes 12.8 seconds, and that should give you 2,570 meters. You got it? Mm-hmm. Nice. That concludes the Physics 111 exam review. Okay, I hope you liked it. Please subscribe and watch my next video, which is going to be, right after this, on the exam review for Physics 121.